Good evening, everyone. My name is Scully McLean and I am the Regional Agriculture Land Care Facilitator for the Limestone Coast Landscape Board. Welcome and thank you for watching our fourth webinar in the Healthy Soils series, Improving Productivity on Sandy Soils. I would like to acknowledge and respect the traditional owners of the ancestral lands of the Limestone Coast region. Potterwich to the north, Jarradwajali to the east, Bowendick to the south, and Meantung to the west. We acknowledge elders past and present and respect the deep feelings of attachment and relationship of Aboriginal peoples to country. So, as you know, I'd like to welcome back our presenter for tonight, Dr Melissa Fraser. She is a senior consultant for the Primary Industries and Regions South Australia and has worked on agricultural soils since her days at the University of Adelaide Roseworthy campus, where she studied a Bachelor of Agriculture. Mel has travelled and studied in Canada and has lived and worked in the Northern Territory and Queensland. In 2005, Mel commenced her PhD in soil science, exploring the soils of the Avenue Plain near Killara and the impact that the Fairview Drain had on the local water table and the expression of salinity and acidity. Tonight, Mel is like a kid in a candy store as she gets to talk about one of her passions, sandy soils. We are very lucky to be able to hear and learn from her local knowledge and experiences on the Limestone Coast. Thank you, Mel.
Thank you, Skyly, and thanks everyone for joining me. If you see me look over like I am now, I've got my control panel on the screen next to me so I can see what's going on over there. Hopefully nothing freezes or fries on us tonight. I know the power has been out in various places across the Limestone Coast today. No doubt you are all a bit fried after a week at home in lockdown watching things online. So again, thanks for coming along tonight when you could be doing something else outside of the house. Anyhow, tonight I am here to talk to you about improving productivity on sandy soils because we've got a lot of them in the southeast. So if we go back to, I guess, webinar 1 and 2 and 3, which have been delivered so far back before the school holidays, I finished up webinar 2 by sort of providing that overview of what makes the soil fertile, and really, you know, it comes down to its physical and its chemical and its biological properties and the way that these properties relate with each other and function together as a system. And of course, we want our soil structure and our stability and porosity to be good. We want water to be out and air to be able to get in and out of soils, and plants to be able to grow their roots and explore through soils to access nutrients. We want our pH to be in the ideal range, and we don't want any toxic elements, and we need enough nutrients to meet the purpose that we want our soils to serve. You know, active and diverse microbial communities, and obviously the presence of our ecosystem engineers like worms and dung beetles and ants and termites, you know, depending on what environment you are. So, you know, those are all the things that make a soil fertile. The challenge with that is we have a lot of sandy soils right across the Limestone Coast in the district. There's about 2.7 million hectares of land across the Limestone Coast, and sort of 45% of that is taken up by our Group G, our sand over clay soils, our Group H, the deep sands, and our Group I, these highly leached sands, which are down around primarily around Mount Gambier across to the border. So we know we have a lot of sandy soils across the region. In the upper part of the catchment, I guess they're mostly used for cropping, broadacre cropping, or more so used for cropping. And as we head south down through the Limestone Coast, you know, obviously we see a lot more grazing and pastures, but also things like potatoes and forestry as well on our sandy soil. So really important soil from an agricultural perspective for the region, but they come with their challenges. We know that sandy soils right across southern Australia, from Western Australia right across through into New South Wales, that sandy soils can often possess a range of different constraints. You know, water repellence is one of the major ones, and you might have seen the impact of that this year if you've been driving around in the northern part of the district. We had a very dry start to the season and patchy establishment and emergence of our crops as a result of water repellence that stops water from getting in and really has an impact on the germination of crops and pastures. Our sandy soils can be quite prone to either developing acidity or can be naturally acidic to start with prior to farming. We know that they're prone to the development of high soil strength, and they can be easily compacted. And once they're compacted, because they don't have the ability to shrink and swell, they stay compacted unless we actually physically disturb them. We know that they are naturally low in nutrients. You just remember that most of the sands, like the sand you can see here, the sands in the southeast have been derived from the beach, from the ocean, as the ocean has retreated over the course of the last 800,000 years from the Narracort Range right back across to the current coastline. At the moment, all of the sand dunes that we've got through here and the sands that have been blown across our landscape have all blown from a beach dune at some point over the course of the last, like I said, 800,000 to a million years. So if you can imagine, if we went and tried to grow a crop at the beach at the moment, it's not going to be very successful, because those sands generally are, inherently lack any fertility that we need to actually grow our productive crops and pastures. We know as well that these soils have low water holding capacity, so they're generally very free draining, so we struggle to hold moisture in them. And we also have this emerging problem in some places as well with salinity, which in some cases is caused by, position with the water table, but we're also seeing, saline seeps pop up, through the mallee, and we're starting to see some areas of concern, I guess, more in the northern part of the limestone coast, up to this, Yamali Canal and through that region, across to Meningie. And I'm also starting to see it as well under irrigation and sandy soils too. So I guess it's one that's really should be on your radar. And like I said, it's the combination of all of these, chemical and physical and biological properties that determine a soil's fertility. And we have these major troubles. And the problem is that very rarely do these constraints occur in isolation. Usually we'll have at least two, if not more. And in the example you'll see here, this is just a range of some of the sandy soils that have been explored in the Sandy Soils project. You'll see anything in my slides that has this little serial notation next to it is information or figures which have come from the GRDC project, increasing production on sandy soils and low and medium rainfall areas of the southern region, of which I'm a member on that project. So you can see from 5 of these different soils across, these are from the South Australian Mallee, Victorian and New South Wales, that we have a range of different constraints which occur in the profile. So, in this particular case, we've got a hard setting, and then we have a nutrient desert underneath, so there's no nutrients. We've got a combination at this particular site of repellence and compaction, again, no nutrients. Get across to New South Wales, and we have some pH stratification, hard setting, and then these sodic layers underneath, which then have poor soil structure and can have some drainage issues. So we know that when we get these constraints, like I said, they rarely occur in isolation, and the combination really leads to poor plant water use. And that's true for both our crops, our annual crops, and also our pastures as well. The consequence of that, of course, is that we end up with low surface cover. We can develop very fragile surfaces, which are then prone to erosion through water and wind. And we can also see weeds then really start to proliferate and take off in places where our crops haven't grown. They can be quite opportunistic in actually surviving in some quite harsh conditions, and that can make them difficult to control. So I guess the question is, for those who are joining us, I know that if you're a farmer and you do have some sandy soils, I guess the question is, is your sandy soil fit for purpose? And that depends on what you're trying to do with it. Are you trying to grow potatoes or forestry or crops or pastures? And is it functioning at its full potential? And we know that a lot of the sandy soils in this region actually probably aren't. And if it's not, then what can you do about it? So I guess I'm going to sort of step through some of the things that I would do in terms of trying to identify and diagnose the constraints in sandy soils, and then some of the things that we can do to actually treat those constraints so that we can improve the productivity of sandy soils right across the limestone coast. So I'm actually going to run you through a bit of a hypothetical scenario. So I think it's useful to actually test things in the real world. And so I thought I would actually pick out a paddock. So in this case, I've picked the problem paddock. You can see it here identified with the red triangle. And below that actually is a photo that I grabbed from Bullabur. It's from a couple of years ago. It's from 2019 in the Mallee. And in fact, the paddock that you see here is also selected from the Mallee too. So a bit more extreme than what we get here, given it's lower rainfall. But I guess we've got the capacity for any of these problems to develop and occur here as well. So this particular problem paddock You know, it's bared out in the dry years. There's been some obvious wind erosion. You can see this, you know, mustard plant here, which thankfully has got a root system which has held onto some soil, but you can see the amount of erosion that did actually, wind erosion that did occur through the mallee with those very dry years of 2018 and 2019. You know, we commonly see that, you know, in this particular case, you can see these sand dunes through here, which are quite bare, but, you know, usually these paddocks will still produce well on the flats. Had some problems growing legumes in here. We struggled to get a crop established up on the rises. It appears to be getting worse. And the neighbour's crops always looks better than mine. And so that's our hypothetical scenario for tonight. And I just thought we'd step through, I guess, diagnosing the constraints in a paddock like that, and then thinking about what the treatment strategies might be to improve productivity across the whole paddock. So where to start? Well, I'll tell you where I start. I always start from space. So I'm not sure what kind of platforms you're using to access aerial or remote imagery, but the one that I use is called Erosion. It's actually a free application. If you have a Gmail account, then you can sign in. If you don't, then make one, because it's absolutely worth it. What you'll find in this application is it was actually developed to make to help the irrigation industry make better irrigation decisions. But what you'll find in here is a whole heap of free imagery, dates right back to 2003, the satellite imagery that goes around every 7 to 10 days and captures both an image, so you can see the actually surface if it's not cloudy, and then also the NDVI, the Normalised Difference Vegetation Index, which gives us an indication of how much greenness there is above ground. And this kind of imagery, it's free, it's amazing. You can go right back, you can mark out your paddocks. And so as you can see, I've got 121 fields marked out there. All the paddocks that I work on with my work, I mark out and I keep an eye on. So definitely recommend you head over to that website and sign yourself up if you haven't already. So if we have a look through the imagery here, you'll see this is just the base layer image. If we and you'll see I don't have anything selected on this side at the moment. If I select the Sentinel image, so that's one of the satellites that has a 10-metre pixel resolution, from March 2020, we can see that there's quite bad erosion which has happened in this paddock. But you can see the neighbour's paddock across the road doesn't look as bad. So we know we've got a bit here. There's also some pretty bad stuff to the east, that would be to the west. So it looks pretty ugly. It doesn't look great. If we zoom right in, we can actually see that that sand has blown across the road. And of course, you would know that if you're a farmer in this district, if this is your paddock, you'd be driving through that sand on the road. So again, this imagery is free and it can really tell you a lot without even leaving the office, which is handy if we're locked down. If we go back to September, I now want to know how long has the problem actually been developing. We go back to September 2019. Again, this is the NDVI. You'll see I've got NDVI ticked here, and so it shows me above ground greenness. And so again, here's the neighbour's crop looking pretty handy right across the dunes and also down on the flats, and mine not looking quite as good. And we've definitely got these bare spots. So anything in brown and yellow means there is no above ground green biomass. So we're in a bit of strife here, given that it's the end of August. And if we have a look, if we go back then to January in the same year, we can start to see, these dunes were blowing then. If we go back to February 2018, so we go back 12 months, we have a little bit of erosion across the top of the hills, but certainly nothing like it was. So we can, from that kind of picture, and here we are in February 2017. So we know that most of this damage has occurred over the last couple of years, that 2018, 2019 season. Prior to that, we weren't tracking too bad, but really the paddock's fallen over pretty quickly. And clearly the neighbour across the road's been doing something different to us. It's also really handy sometimes to zoom out and see how you're tracking in comparison to the neighbours or to other places in the district. And this is just an example of that and how useful this can be, particularly in a sandy soil landscape. It's also really great after fires. You can see fire scars. You can see we could track the clay spreading that happened across the upper Limestone Coast or through the Sherwood district after the Sherwood fire, for example. So it's a really great little tool. So my next step, I've had a look through and I've determined that really we've had a lot of degradation occur in the last few years, and it's primarily on those hills, and there's definitely something different between our place and the neighbours. The next thing I would do is zone it up. So it's really important that we do zone it up, because we see that, clearly we've got these, deep sand dunes, I would say here. These are probably not quite as steep. We have these small interdunal kind of flats, and then I would suspect that this would be a heavier flat, you know, down off of the crest of this dune here, going by the above ground biomass that we've seen growing there, be typical in this sandy soil landscape. So this is the first step I would do before I go trying to solve any problem, either with a sandy soil or a clay, is see what I can see from space. And always before I head out in the paddock, have an idea of where I'm going to sample from, where the good bits are, where the bad bits are, how they've tracked over time. And so I've already got an idea of where I want to go to and sample. So the next step then is diagnosing our constraints. So within each of those individual zones, you really want to get a feel for what constraints are present, what depth in the profile they're present at, and how severe they are. So the first of our constraints, the one that's one of the easiest to see, is water repellence. And you can see here just some beads. This is actually pH indicator dye on the surface in this particular instance. But down here, you can see this is a picture I picked up today off of Twitter from Matt Howe, up at Melanol, close to Meningie. And you can see we've got quite good canola establishment here on the right, and on the left it's really patchy and we've got lots of bare spots. This is really common on a water repellent sand. The reason it's so good on the right hand side is because this particular paddock had a test strip put through it in 2016, I think it was, with a Plaza plough, which actually inverted the surface layer and buried that water repellent layer. And so we overcame water repellents in that case, and here we are all these years later with you know, really good establishment. So water repellence is caused by plant waxes, primarily on the sands of the grain, on the grains of the sand, and essentially they become hydrophobic, so they actually repel water, and it's really difficult for water to get into the soil. They don't wet up uniformly, and we know that, you know, when we plant crops, for example, into a dry water repellent sand, that our establishment can be pretty poor. And I spent a couple of weeks on the EP in July driving around over there, and unfortunately we saw the impact of a really dry sowing. There's lots of patchy establishments, so I'm grateful that most of the states had a good drop in the last few weeks. The way that we detect the water repellence and its severity is by conducting a water droplet penetration test. And essentially we drop water onto the surface and we time how quick or how long it takes for those droplets to penetrate or infiltrate into the soil. So if you wanted to do this test, it's recommended that you collect some soil samples in a 0 to 5 and a 5 to 10 centimetre depth layer. So again, if we went out into that paddock, into our problem paddock, I would collect samples across each of those zones and I would bulk them together into the same bucket for a 0 to 5 and a 5 to 10 centimetre layer for zone 1 and zone 2 and zone 3 and zone 4, and bring them back. If they're wet at the time, you can leave them just on a windowsill to dry. Or in a warm spot but not hot, and let them dry out, and then conduct this test. So it's pretty straightforward, and I've actually got a video here. I had a crack at actually demonstrating some of these tests for you. So you'll see that I've just set these up. In the background here we've got again this hypothetical, so we've got zone 1, zone 2, zone 3 and zone 4 soils. And you'll see I've just got a medicine drop from a chemist, and I've got demineralized water in there. In the background, I've just got the timer on my phone, and you'll see I'm just dropping just a few drops of water onto the surface. And so you can see that in here in zone 1, the water is still sitting there. In zone 2, it went in. It did hesitate for a second, but it did go in within 5 seconds. Same here. And in our zone 4 soil, that water is also soaking straight in. So you can see in the background, I'm up to 33 seconds here already. So to determine the severity of repellents, if it goes in within 5 seconds, then it's non-repellent or the soil is wettable. If it takes more than 5 seconds but less than 60, then we know we've got mild repellents. If it's 60 to 240, then it's moderate. And if it takes more than 4 minutes for this water to infiltrate, then we've got severe repellents. So you can see this is a really simple test. It doesn't cost you anything but a bit of time. And it can give you a lot of information really quickly. Now, what you'll see here in this second dropper that I've got there is actually a wetting agent, which is mixed up at the right concentration. So if you did put a wetting agent out at sowing, if you were trying to establish a cereal crop, you see that those droplets infiltrated straight away. So they break the surface tension of the water, and so it can infiltrate even though the soil is hydrophobic. And we know that that can improve crop establishment if we use those wetting agents at sowing. At the lab, if you wanted some more quantitative numbers, you can send those soil samples to the lab and they would conduct what's called the molarity of ethanol droplet test. It costs about $10 a sample and they'll send you back some numbers, and then you can determine or see just how extreme the repellence is in your particular sands and how it's changing over time. So the next constraint that I would go on to diagnose then is acidity, and we do know that there are some sandy soils which are now developing seeps, which can also be alkaline, but typically our sandy soils are acidic, and so that's what I'm going to focus on today. I'll talk about alkaline soils in our next webinar on clays. So we know that acidity can develop in our sandy soils, particularly under cropping. It can be exacerbated with the application of nitrogen fertilisers, obviously with product removal as well, particularly if you're removing hay, and also from the production of acids from plant roots. And we also know that it can be exacerbated in high rainfall environments with lots of leaching. So we've kind of got the prime scenario here for developing acidity under our, particularly under our cropped our cropping systems. So we know that our surface acidity can actually extend into subsurface layers, and in this case I'm talking about the surface being the top 10 centimetres and the subsurface being 10 to 30 centimetres, and then the subsoil 30 and below. If you've got subsoil acidity, unfortunately there's not a whole lot we can do about that because it's hard to get there, but really we want to look at acidity not just in the top 10 centimetres but really through this whole 30 centimetre zone, because we know that it can stop root exploration. Aluminium can come into solution, which is toxic to plants. Biological function can slow or stop, and we get poor utilisation of our nutrients like nitrogen and phosphorus. So acidity is pretty extreme, can have big consequences on your production, and really it's better to prevent than cure. When we measure pH, we recommend sending a sample to the lab, and you'll get back a result which will be measured in both calcium chloride and in water. And our recommendation is to use the calcium chloride value. So in the surface layer in the top 10, you want to keep this above 5.5, and in this layer above 4.8. Now that's a well and good, but I'm all about trying to get answers on the day. So there are other things that we can do as well, which I'll show you in a sec. One of the emerging problems in South Australian sands or in sands right across the southern region is the development of stratification, which is discrete bands of acidity. And you can see in this particular image that we have this sort of purple colour on the surface here. So this has had some pH indicator dye applied to it, this soil. And because there is lime applied to this soil, you can see all the lime is sitting here in the top inch, and below that we've got this orange colour, which is the colour of the soil. It's actually acidic below that. So we know that if we do apply lime, for example, and we don't incorporate it, or if we've got all of our stubble sitting on the surface, and of course we're in no-till systems now, so we don't get any subsurface mixing. We put all of our nitrogen in a band in the same position most years. We can actually get these discrete bands of acidity show up, and you can see that here. This is a dig stick. It's a really great tool if you haven't got one. They're only a couple $100. You can see here in the surface, we've got these sort of purple colours, purple and green. So this soil here is neutral in the surface, and then we get this really, extreme and severe band of acidity in these bright yellow and green colours in the sort of, 5 to 15 zone. And below that, we see the pH start to come back up again. Now that's really common. Now, typically we would sample the soil in a 0 to 10 centimetre layer depth. And so if we took that soil sample, because we take most of our soil samples, of course, to make nutrient recommendations, not to make, diagnosis for acidity, that soil sample would get mixed up, the alkaline stuff on the top with the acidic stuff on the bottom, and it goes off to the lab and it comes back and you get a pH back at, 5.8, and you go, oh, well, I'm all good. But really, it might be 6.5 in the top 5 centimetres and 4.8 below that, and you've actually got a problem. So it's really important to go looking for stratification if you are seeing some of your yields start to decline. So to diagnose acidity in the paddock, to get a pretty quick indication of whether acidity is an issue in your soil types or not, you can do that with one of these soil pH test kits. So you're only $20 to $25, pick them up from the hardware shop usually, or the plant nursery. And I will play for you as well. Here's our soils again, our zone 1, 2, 3 and 4 soils. And it's pretty simple with one of these kits. When you do measure the pH with one of these kits, the pH in this is equivalent to the pH in water if we measured a 1 to 5. So you want the pH on one of these kits to be above 6, 6 and above, because that's going to be equivalent to about a pH of 5 to 5.2 in calcium. So we really want it to be in these dark green and purple colours rather than down in these bright green and yellow colours. Again, within each zone, you want to take some samples and mix them up. You can either take samples and mix them together in a bucket, the same as I explained before, or I like to just dig a pit just with a shovel, expose a soil face. You can squirt this on straight down the profile and puff the powder on, and it will show you, how the pH changes down the profile. But this is another way to do it. Again, here's our water repellent sand from zone 1. You can see the indicator dye there is not infiltrating that soil, so I had to give it a bit of a mix to get it to react, but the others have all gone in okay. So again, just pop on the indicator dye, the liquid, and then I'm just going to puff the powder on. Here it comes now. It's barium sulfate, so it develops a colour when you pop it on top of the liquid. And I've actually got some ratings here in terms of severity. And if we're looking at the acid end, which these soils are going to be, if it comes up on the card in the 6.5 to 7.5 colours, sort of through here, then we're in the neutral and ideal zone. And then once we drop below that on the card, the 6 to 5.5 and the 5, we're really getting into this mild to moderate to severe acidity, and something really needs to be done. When you're out taking these samples, I recommend you pop some in a plastic bag as well, so that you have got samples retained to send to the lab for analysis. So you can see those colours developing there, and quite simply, I'll pop up with a card here in a sec. And we can use this card just in natural light, not under fluorescent light. Take your sunglasses off, and you just want to line this up. You can see that I did actually get an orange pH recently out at Bull Lagoon, which was a bit of a surprise. I nearly fell over when I saw it. It's the first one in a way years here. But so we can see there in zone 1, we're at 6.5, so we're in that neutral. Zone 2 is a 6, so we're in that sort of mild acidity. We're back to neutral again in zone 3. And here's our zone 4 soil. And if we run down through the colours, it's lower than a 5.5. And I'm checking here to see whether it's 5 or 5.5, and I've settled on 5 in this instance. So I'm saying that the soil in zone 4 is actually severely acidic. So this tells me that down there we've got a problem. Remember, up in zone 1, the major problem was, water repellence was a major problem in zone 1. And here we are with a bit of acidity developing in zone 2 and really extreme here down in zone 4. So I know this is a hypothetical scenario that I've set up for you tonight, but we absolutely see this kind of variation in the real world, and it's really important that you do sample strategically across your paddocks and with depths in the soil, because otherwise you spend a lot of money and time getting results back that don't mean anything. Like I said, I would with those kinds of assessments, and with a soil like this, we can actually use this kind of in paddock assessment to help us make a really good decision about what depths to samples to send to the lab. So in this particular case, I'd recommend sampling a depth increment of 0 to 5, sort of pick up that kind of more neutral to alkaline surface layer, and then a 5 to 15, and then a 15 to 25. And you collect 10 to 15 samples from each zone, mix them together, take a subsample in a bag and send it off to the lab. They're going to measure the pH in water and in calcium chloride, but it's also worth requesting an aluminium test, also in calcium chloride, so you can see whether you've got aluminium, toxic concentrations of aluminium in the soil. Texture is also useful as well, so that you can make a really good lime recommendation, and also organic carbon is also important for that. You might be hearing you're thinking, oh, gee, that's a lot of money. If we're collecting samples from 3 different depths across 4 different zones, and how much is that going to cost? I can tell you can save yourself a whole lot of money by investing in this kind of strategic sampling, because it means that we're going to put the right rate of lime just down in zone 4 where we need it, and not across the whole paddock. So it really is worth spending a bit of time and doing your homework or your groundwork before you call up the contractor and get the truck with lime on its way. One of the other really useful tools for assessing or diagnosing acidity is actually using mapping. So there's a couple of different mapping technologies. There's one that takes samples on the go and actually records and measures the pH while it's traveling, and that's called a Veris mapper. This is an example of some grid sampling. So in this particular case, this paddock, it's 32 hectares. It's been broken down into grids of 2 hectares each. And within each grid, 8 soil samples are taken, 0 to 10 in this particular instance, and bulked together and sent to the lab. And then we can convert that information into a pH map. And so this is exactly, this is a greater layer of detail, I guess, than what we were sort of crudely doing before with the zones that I'd identified. But in this particular case, it picks up this corner down here, which is a clay soil in the corner, which is more alkaline, and then this area of deeper sand through here, which is high productivity, and which has become really acidic. This is pH and calcium. And then this the pH comes back up again through the sand on the top of the hill here. So again, these kinds of maps then can be put straight into a spreader contractor's computer, and you can put a variable rate lime out across the paddock on the go. So some of these mapping technologies provide a really great indication of the variability you've got, but it's really important that you go and dig deeper and get back out and ground truth the maps as well, and make sure that you are looking particularly for those stratified bands, which might actually be much worse, and any acidity which is extending below 10 centimetres. You can also diagnose acidity sometimes offsite, and again, I come back to my satellite type imagery to help me out here. Be mindful that not all crops are susceptible to acidity. You can see here this one particular paddock, which in 1 year, I think this is 2018. We've got pretty uniform above ground green biomass in September. And the year after that, we've got, these really patchy areas that, aren't producing very well. And essentially the story here and what explains that is the fact that in this year, the crop was wheat, and in this year, the crop was beans. And we're seeing beans right across the Limestone Coast are one of our really good indicator crops for the development of acidity. They really don't do well in an acidic environment. And you can see here that in terms of a tolerance to acidity, that, are highly tolerant, crops and plants are things, no surprises that, ryegrass fits up here, very tolerant to acidity, wheat, and then we've got peas in the middle, and then we start to see some more, sensitivity as we get to our canola and our barley and our faba beans, and of course lucerne will drop out as well if we've got the development of acidity. So again, knowing the crop rotation can also be really useful if you are looking at some of these sort of spatial tools, spatial and temporal tools for looking from space to see what might be going on. Here's an example, classic as well, of the development of acidity on the deep sand at the top of a hill is the lucerne pasture. You can see here we've got some sorrel, which is a really great indicator species, and of course silvergrass as well. Those types of weedy grasses will pop up and do really well in an acidic environment, and the lucerne will drop out. So these are the kinds of things that you can look for in the pasture situation too that might tell you that you've got acidity at play. Again, I'm going to touch on electrical conductivity or salinity and acidity in our clay webinar, but I thought it was just worth reiterating again that we are starting to see some issues with salt in our landscape, particularly I think as our rainfall distribution and volume is changing, and our water tables have dropped as a consequence of that, and the drainage networks, and that does have implications for salts and soil structure. So if you did suspect that salinity is an issue or an emerging issue, again, you can do this at home. You can measure the EC, so a 1 to 5 solution of soil to water. 1 to 5 soil, yeah, I got that right, soil to water. And soil samples collected from within each zone. It's about $200 for one of these EC meters, and commonly they do measure pH as well. And yeah, mix up a 1 to 5 in a jar with demineralized water, and you can measure the EC sort of on the spot. This is something you can do in the same day. And then again, determine the severity of salinity and the effects that it's going to have on different plant types as well. At the lab, again, you can send these off, these same samples that you might have collected for pH or water repellents, and request this test, and they're going to do the same thing. They're going to measure it in a 1 to 5 solution of soil to water, and then they're also going to measure the texture as well, so that you can make some good recommendations about what kind of species are going to be suited if you do have a salinity issue emerging. Soil strength, hang on. As I mentioned at the start, high penetration resistance or high soil strength is another issue that we can get in sandy soils. We know that soils, in terms of their resistance to failure, so if we push something through them, it's going to be easier to push a rod through when the soil is wet than when it is dry, but it's also going to be harder to push it through when a soil has a high bulk density. So when we've got all of those soil particles packed close together and we don't have much pore space. And that high bulk density can come together, it can occur either naturally or it can be induced by, farm machinery and livestock traffic and what have you. And if we're talking about soil strength, the way that we measure that is with a penetrometer, and we talk about the penetration resistance, and both of these issues can inhibit root exploration. So it's really important that we know if we have got a physical constraint in the soil, because it can stop plant access or root access to soil moisture and nutrients through the season, and we end up with crop roots that are only growing in the top 15 centimetres of a soil that's a metre deep, because it physically isn't strong enough to push down through the soil. Now, that isn't true for all sands, and there's an example here again from the Sandy Soil Project of some penetration resistance values or soil strength values using a penetrometer. And so at this particular site here at Wakery, we know that soil strength is moderate when the penetration resistance exceeds 1.5 megapascals or 1500 kilopascals. Once we get above 2.5, then we know that root growth is really going to slow. And once we're at 3.5, really roots can't push past or through that soil at all. So we know we've got an extreme problem in that case. In this particular case, if we look at Butte, for example, we've got our sort of cutoff here at 2,500 megapascals. The black line here that you see down through the soil profile from the surface at 0 centimetres down to 70 centimetres, we're actually below that the whole way down. In Oyen, we've got a big bulge which starts at sort of 20 centimetres and peaks at sort of 35 to 40 centimetres and then actually gets better again. So there's a real indication here of either high soil strength as the soil dries or a compaction layer at that depth. And at Wakery, it's actually a bit shallower. So we cross that line at only sort of 12 centimetres. So again, this is the point where roots are going to struggle to push through, and it's happening really shallow in the soil. So, potentially some compaction here from traffic. But it doesn't extend as far, so it's not quite as bad. So again, it's really important that we know if we have got a physical constraint, where in the profile does it occur, where does it start and where does it stop, and how bad is it? Because that's going to inform the kind of strategy that we use to overcome or treat that physical constraint. So we're going to use a ripper or a spader, or we're going to go delving. These are the kinds of things that you need to know before you put a machine in the paddock. So the way that we measure this in the paddock is with a penetrometer, and here's an example here of just a cone penetrometer. It's got a pressure gauge on the top, so you can see how much force is actually required to insert that penetrometer into the soil. You must do it into wet soil. We know, like I said, that soils that will increase in strength as they dry. So this is actually a perfect time to get out and do them. Maybe not this week, but maybe next week. We've got some more rain coming. You really want the soils to be at full capacity. So after a good bit of rain with 24 hours to drain, go out and take some of these readings. And if you see that penetration resistance come up at a certain point in the profile, you can be fairly confident that you have got a compaction issue at some depth, and you can measure where they start and stop. And you can see, how bad or severe that constraint is, and then what its likely effect on root growth is going to be. At the lab, if you want a bit more certainty, we can measure things like the bulk density, and this is the way that we do that. It's by collecting the soil in a known volume and then getting the mass of that soil in that volume, and so we can work out the bulk density. Once it goes above 1.6, we know that roots will start to struggle to push through those soils as well, particularly as they dry. So another really great another constraint that really warrants diagnosis. So I didn't worry about measuring the EC in those 4 soils because I didn't see any signs in the paddock that salinity was an issue. But if we have a look at some data that I've got here for penetration resistance, in this case it's in kilopascals, I've got my severity rating here as mild, moderate, severe and extreme as we go from 0.5 to 1.5 and right up to 3.5. Apologies, that's in megapascals and this is in kilopascals, so you'll have to wrap your brain around that tonight. Sorry, it's late. But I've got them colour-coded anyhow. And so as zone 1 and 2 and 3 soils, we're all sort of down here in this sort of mild kind of soil strength right down to sort of, 30 centimetres. It's only once we get below 30 centimetres we go into moderate, and then from 35 we're into severe, and then we eventually pop into extreme down at 45 centimetres. But zone 4, which, from the outset we've said was our loamier soil down on the flat, heavier soil type, higher producing historically, perhaps it's got a bit of clay in there as well. We actually see the penetration resistance in this case actually be much higher. And, even here at 15 centimetres, we're already into the moderate. We're in the severe at 25, and we're in severe at 25, and we crack into the extreme here, at only, 25 to 30 centimetres. So really, root growth in this case in that zone 4 soil is really constrained to the top, 15 to 20 centimetres. So we haven't got the capacity to explore very far, which is fine if we happen to get a really good rainfall year and we keep topping up the profile. But if we get a pinch at the end of spring and we really want our roots to get down and explore those deeper subsoil layers, then it's important that we, diagnose and overcome these physical constraints. There we go. That's the zone of most greatest influence that we're looking at. Like I said, also at the start, we know that our sandy soils are inherently, pretty infertile. They don't naturally contain a lot of organic carbon, and that can have an impact on their biological cycling as well. But if you wanted to get a feel for how, fertile your soils are, there's some things you can look for. Soil colour, the darker the better. Have you got worms and dung beetles and ants or termites, depending on your environment? Are those bugs there and visible, and are they doing something? Things like your indicator species. So like I mentioned before, your sorrel and your silvergrass, popping up and proliferating where other other crops or pastures won't persist anymore. But really, to get the best feel for what's actually going on, you want to take a soil sample in a 0 to 10. Absolutely, the surface layers at the start, but hopefully deeper as well, depending on your system. You want to take these within each zone and send it off to a lab. And, of course, you're going to get a whole range of information if you do that with one of these types of soil tests that come back. It will tell you about the soil's, natural inherent fertility in terms of its cation exchange. You'll get the pH, values. You'll also get the range of nutrients, both the macros and the micros, with the trace elements here, and then a feel as well for salinity, and then, the balance of those cations too. So stack of information you can gain. Again, in this case, maybe 4 soil samples from across the paddock, but at least and can detect nutrient deficiencies or, build-ups in some cases as well across, these paddocks which have got really variable productive capacity. So if we're going to summarise, if we've gone out, we've actually, here's a reminder, this is our paddock. Here's our 4 different zones. We've got our really deep sands, which have eroded and haven't established well for the last couple of years. Sands that aren't quite as bad, and then our sort of interdunal type, little flats, and then heavier flats in zone 4. If we summarise the diagnosis, across those different zones, remember in zone 1, we found there was really severe water repellence, and the other sites were wettable. From a pH perspective, we were neutral and mild in zone 2, neutral in zone 3, and we had that severe acidity down in zone 4. The site was non-saline. I know that from a lot of the work that I've done in this patch that we can see things like phosphorus actually start to build on these deep sands, because we know we've only been pulling off a quarter of the yield from them, but they generally get fertilised the same as the potential for the whole paddock. And so in some cases we see that phosphorus particularly can build on some of these sands and actually get depleted down on the flats. So in this particular case, I'm saying that we've got adequate all adequate nutrients across the zone 1 and 2 soils, but where we've had higher productivity and product removal, we're actually depleting the phosphorus reserves in this case. And we know that our soil strength from those measures that I had, goes from mild to moderate across most of the paddock, but down here on the flat, we do have this severe to extreme, penetration resistance, so high soil strength. So well, that's all well and good, but what do we do with that information now? You spent the time to diagnose it, and so what does the treatment actually look like for a paddock like this, so that we can optimise the productive potential right across, or realise the productive potential right across these variable sandy soil landscapes that we are all blessed with. So when it comes to treating constraints, that's what I'm going to go through now. So with water repellents, we've got a couple of different options. Like I demonstrated before, there's that sort of wetting agent option, which is an annual strategy, things like sowing configuration. We know that sowing on the row or near to last year's crop row, you will get better establishment because water generally runs down those old root channels. Generally, the soil will be wetter in there than in the mid row, so that's important. We can also adjust for things like seeding rates. So we do have these annual, what we would call mitigation strategies. They're generally low cost, but they need to be reapplied. Then there's strategies like soil mixing. So I showed you the example at the start with that canola, which had germinated really well in the soil, which had been plozza plowed. So essentially this is a plozza plow, and what it actually does is mix and dilute that surface layer and sort of essentially bury the water repellent stuff that's at the top and put it down lower in the profile, and so we can get better establishment. These types of scenarios are generally cheaper than a permanent solution like clay spreading, but they don't offer a permanent solution. Well, actually, we don't know. We had 6 years response there on that other one. But if you're looking for a permanent solution to water repellents, then we know that clay spreading can do that if we put clay onto the surface and we incorporate it. But I would say that before you go opening up any soil pits, do just be mindful that when water naturally flows across your property, you can't go digging pits where water would naturally flow through creek lines, and also be conscious that some grasses and sedges and small trees are native vegetation, and you don't want to get caught up clearing native vegetation in your pursuit of clay to spread across your farm. So it's always worth having a chat to the Limestone Coast Landscape Board. They can advise you on areas that are safe to excavate. When it comes to treating acidity, really the message is lime it or lose it. And we also know that incorporation counts. So I showed you that image from the start of all that lime sitting in the top inch. We know that lime will really only move about 1 centimetre per year if you leave it on the surface and don't incorporate it. So if you've got an issue, down at 7 to 10 centimetres, it's going to take 7 to 10 years for any lime to get there. So, this is one of the cases where we would actually say, know all of your constraints and think about the opportunity to treat multiple constraints at once if you are going to go in and, disturb or mix lime into the soil. We know that clay spreading with alkaline clay can help to neutralise acidic soils, but if you've got acidic clay, then it won't. So again, if you're going to go clay spreading, open up some pits, make sure you've got the proper approvals and clearance, and check to see what the pH of that clay is, because you might actually be exacerbating a problem. And we know that even once you've rectified an acidity issue, that soil acidification is a natural byproduct of our intensive, sort of cropping system. So even once you've rectified it, you'll need maintenance lime, probably every 5 to 10 years, depending on your rotation and your productivity and your end use and your legumes in your rotation. For more information, head over to the acidsoilssa.com.au website, which has been a project which has been delivered by PIRSA, funded by the GRDC. And there's a whole heap of information in there, and case studies, and also calculators and tools that you can use to look at what acidity might be costing you, and then the kind of lime rates that you can use, and also the sources of lime that are going to be worthwhile to put on at your place to treat an acidity issue. So lots of really great resources there. When it comes to treating high soil strength, this really takes a bit of, should take a bit of your brain space, because there are lots of options, and you can spend a lot of money and not actually treat the problem that you think you've got. Really, that thorough diagnosis of all the constraints is crucial before you select a deep ripping or a deep cultivation implement. We can rip, we can deep rip, there's spaders, plozza plows, offset discs and delvers and all sorts of things, but really what you want to do is make sure you select the best implement for the combination of constraints that you've got. So when it comes to ripping considerations, really ripping is something that you would employ if you just had a physical issue. If the rest of the soil was pretty good chemically, but you've got a compaction issue, or you've got a hard setting issue, and you've seen other people in the district perhaps get responses to deep ripping, or you've seen results from things like the Sandy Soil Project, then deep ripping can help to shatter those subsurface layers which are compacted, and that can help to open up the subsoil and allow the roots and the water, or water to get in and roots to get down to actually extract it again. It's really worth knowing, though, exactly what depth in the profile that say compaction or high soil strength occurs. You want to know how severe it is, and you want to know how deep it goes, because if you've only got an issue to 40 centimetres and you go ripping at 60 centimetres, then A, you're working your tractor too hard, but you actually don't have the working tip of the tine in the right spot to get the best benefit. So things like shank design and configuration are really important. Like I said, the depth of where that compaction is. Don't do it if the soil is too dry. You really want ideal moisture. You got to think about the surface finish. It can be quite rough sometimes, so think about the angles for traffic afterwards. Perhaps a rolling afterwards as well can help to smooth the surface and make it traffic so you can get over it again, particularly with your planting and spraying operations. Be mindful, of course, of the timing and the erosion risk with any of these types of physical interventions. But also ask yourself, do you need mixing? Because if we actually want to mix lime in at the same time, then a deep ripping operation isn't going to do that. What you can see down here is an example of what's called an inclusion plate. It's essentially a funnel which bolts onto the back of a ripping tine, and as the tine goes through the soil, the surface soil in the top 10 centimetres can drop down through that funnel and actually create a bit of a band or a sausage of topsoil down into the subsoil layers. And we're seeing some benefits of that in the research work that we've been doing. We're still trying to unpack exactly what the mechanisms are that drive that, but we suspect that both the longevity of the response, so how long the response to ripping lasts, and also the magnitude, the types of yield gains that you'll get in some cases have been better with the use of an inclusion plate when it's set up and used right. So it's an emerging space, and there'll be more information to come out on their use in the next little while from the Sandy Soil Project, so look out for that. If you haven't seen a spader before, essentially it's a bit like a rotary hoe, but with a much slower revolution speed. You'll see it has spades, which rotate on this central shaft through the soil, and essentially it's a bit like a dog paddling through water. And so it will take soil from the top and take it down into the soil, and it will take soil from the bottom and up to the top. And if you imagine, you end up with a bit of like an egg carton shape incorporation, and you can actually see that here in this photograph, where the grey topsoil has been taken down to 30 centimetres at the tip of those spades, and then in between we don't have as much mixing, but we have got uniform decompaction, if you like, through that whole top 30 centimetres. So the spader is really great for mixing if you did need to incorporate, say, nutrients or lime or an organic amendment like compost, and overcome a physical constraint. It's really good at doing that, but only to 30 centimetres. So again, if you've actually got high penetration resistance to 60 centimetres, this machine won't fix that entire problem. But it does also come with its some challenges as well. So again, we have this sort of, you've got to consider the soil moisture. So a bit of moisture in the profile will be good to help the soil pack back down again. There's always erosion risks when we do bury those surface layers. If you do it too fast, you don't get very good incorporation. So of course, the operator that you have is really important for any of these operations. The person driving the tractor can be the difference between a good job or not. But there are some emerging technologies as well, like spade and sow. So we actually spade in the sowing window and sow a crop right behind that, and that can minimise or mitigate some of these risks, and also help to manage sowing depth, because we know that soils are generally pretty soft after spading. But if you've got rocks, that's no good. The spader doesn't like rocks. It also doesn't like stumps. So, it's a great machine, but again, it has its limitations. So you've really got to know the paddock that you're working in and the range of constraints that you want to overcome if you're going to go considering a spader. And again, that deeper compaction, it won't treat that. You may have heard of the Plaza plough. I've mentioned it tonight. Essentially, it's a one-way disc plough. They're rising in popularity because you can generally make them. Most people have got an old John Shearer, one-way plough sitting under a tree somewhere, where you can pick them up for sort of 10 grand. Take off every second gang and then put on one of these Plaza discs, which are manufactured by the Plaza family in Western Australia. And essentially what you get is sort of this crescent-shaped incorporation or inversion of the soil. And so what happens is all the surface soil basically ends up at the bottom and the bottom soil ends up at the top. And so we can bury that water repellent layer. It's very good for that, but you can see that the mixing isn't as uniform through the profile as something like the spader, but it's much cheaper. And as long as you can manage the risks in terms of you know, erosion risk, particularly do it when there's good soil moisture and right ahead of sowing, then it has shown to be quite successful in some instances in South Australia in the last few years. But you also really want to know what lies beneath, because it is such an inversion. If you bring up, you know, if you've actually got really acidic soil at 30 centimetres, you're going to put that on the surface. You're also going to bury, you know, all of that good soil that you've taken, you know, however many years of farming to build up, and put it at the bottom. So you know, you really want to know that you're not bringing anything toxic to the surface. When it comes to nutrient deficiencies, again, you know, we've gone out and we've done our zone sampling, and we know from our perhaps from our yield maps as well, and also from our soil test results, that we have got these differences in the productive potential across the paddock, and we've got some differences in the nutrient concentration in those different zones. Obviously, we can correct those by applying and incorporating specific nutrient packages, either broadcast on the surface, or if you've got the capacity to alter your fertiliser rates at sowing with a zone map, then that's also there's the potential for that as well. We can stimulate biological activity with, you know, by incorporating livestock into the system, also with our you know, rotations, incorporating stubbles or getting stubbles, you know, back at least in contact with the surface, and also with things like organic amendments like compost or litters and hay. Those types of products are usually come at a pretty big cost, and we have seen some big gains with them, but we've seen variable responses, I guess, in terms of the longevity in the sandy soil environment, in the sandy soil project, but that's in as well, be mindful that that's in the low to medium rainfall area. So I think we have got the capacity in the Limestone Coast, because we have got some sources of recycled organics, being this particular example you can see here is from Mulbartons at Pathway. There's a big composting facility there. BioGrow down at Wandillo as well have a large composting facility. So we do have these recycled organics in our district, and we're in a high rainfall environment where we've got a better chance of getting you know, reliable yield gains every year. So I think watch this space with those products in the broadacre and also in our grazing systems as well. I think there's a lot of potential for them in the future. So when it comes down to, you know, to summarise everything, you know, what would the treatments then be for each of my zones? What would I decide to do? Well, I think, you know, for something like, you know, zone 1, where the soil, you know, really the major problem there was severe repellence, we could use a wetting agent at sowing. We could sow on row, or if we had a bit of clay that we could pull out of a pit and, you know, down from the flat or somewhere close by, we could clay spread across the top of that, and probably that hill and all of the others, but not worry about the rest. We could incorporate it shallow. We could go with a lower rate and incorporate it shallow if we just wanted to overcome water repellents, or we could go with a high rate and incorporate it a bit deeper with a Spader if we wanted to overcome repellents and also increase the capacity of the soil to hold soil moisture and nutrients. So there's some decisions that can be made there. There are a heap of resources which I'll tell you about in a minute that could help you work that out. But you know, in zone 2, you know, all we really need here is a low rate lime. Zone 3 was pretty good. And then down here in zone 4, you know, we've got this sort of, you know, severe acidity issue, we've got a compaction issue, and we've also got some depletion in phosphorus reserves. And here, you know, we're looking at a high rate lime. You know, I'd incorporate it with the Spader, and we would, you know, look at getting some extra phosphorus on if we were looking to grow, you know, high productivity crops, for example. So you can see that by spending the time and the money by actually zoning up your paddocks and doing these types of diagnoses zone by zone, we can actually save ourselves a lot of time and money, because in this case, we're actually going to put most of our investment into the best part of the paddock anyhow, and really, you know, look to use more lower cost mitigation type strategies across these sands. Hopefully start to outcompete the neighbour and stop blowing stuff across the road. Again, this is just an example of how knowing that combination of constraints, it really matters. And so this is one of the sites from the Sandy Soil project from the Impacts program. This one again is up in the Mallinong district. So this particular site has severe repellence. It was acidic, and it also has severe soil, high soil strength, and starting from sort of 20 centimetres. So this particular site had already been spread with lime because they knew they had an acidity issue. And so in this particular case, with the treatments that we've applied there, this is a spaded treatment. And so you can see the type of mixing that we got with the Spader here. This is the wheat that we grew, the wheat that we grew there in the first year. You can see the establishment of that crop is uniform right the way down the rows. We've almost got row closure. And so it's done a pretty good job, the spading in that case, of incorporating the lime, of burying and diluting the repellents at the surface, and also overcoming a physical constraint. Where we've ripped the soil, it's done a good job of overcoming the physical constraint. We can see some extra roots growing just here, but we can see most of the roots are concentrated in the surface. We've got this very distinct horizon still, the A1 to the A2. So we know the roots are really constrained up in this layer where the penetration resistance really starts to increase below that. And you can see the patchiness that we've got back here. The crop isn't as vigorous. We don't have as much growth in the crop or row closure, and we can see some really patchy establishment in the background because, of course, ripping overcomes the physical constraint but does nothing to treat the water repellents. So we still had poor establishment in most years with the ripping at this site. We're into our third year now, and it still struggles with establishment. The plotter plough does a good job again of overcoming repellents and also incorporating the lime and overcoming the soil strength in the top 30 centimetres. But because it was conducted in this year when the soil moisture was quite dry, and then we had quite a long window before it was sown, because the surface was so fragile, it did blow and we had quite bad erosion. And you can see that those patches actually still haven't recovered even in their third year. We still have really patchy growth across them. So it's really important to know what you're bringing up and the timing with some of these, the application of some of these treatments. So hopefully that has convinced you that it's worth, diagnosing sandy soil constraints and, zone by zone across your paddocks, and also coming up with those sort of targeted and strategic treatment options as well. So my take-home messages tonight are, we know that sands often possess these multiple constraints that result in poor crop water use, and that's for both our crops and our pastures. I haven't shown you any crop data tonight, but I will point you in the right direction if you're interested in knowing what some of the responses are in your district. But we know that their productivity and their resilience and their profitability can be improved when the constraints are treated. But really, it comes down to proper diagnosis. And we know this when you go to the doctor, you want a proper diagnosis to make sure you're walking out with the right drugs to treat the right problem. And it's exactly the same with your soil. So we really want to know the combination of constraints that you've got, at what depths they occur in the profile and how severe they are, so that we can make really good decisions about the treatments that we employ in the right spots at the right time. And I finished off with this last statement at the end of my last webinar about our healthy soils really provide these vital services to our ecosystems, but not just for nature, but also for humanity. And please nurture them. And I look forward to working with you all in the future and seeing what you do. So a lot of the information from tonight has come from a document that we've recently updated called Sandy Soil Constraints in South Australia, a guide to their diagnosis and treatment. It's currently sitting with the Murraylands Landscape Board. I believe it will be released in the next few weeks. So we'll make sure that will be promoted through the MacKillop Farm Management Group, but we'll also make sure we get it out through AgConnect as well, so that you're all aware of it and can download that document. Throughout that document is links to all of the recent research papers and information that's been coming out of things like the Sandy Soil Project, and also resources like clay delve spade, which can help you make good decisions about clay spreading, for example. And the numbers, of course, have come tonight from interpreting soil test results and also from the soil quality website. And of course, none of this would be possible without the, the collaboration of the growers and, the great team of scientists that I work with. So thank you to all of those. Please come back and join us again on the 18th of August, where I'll be talking about my other great passion, the clay soils down the plains. And I look forward to it. So